Welcome to this Forge College Explainer. Let's jump right in. If you've been following along with our capstone project on implementing secure blockchain structures, you know we're building something pretty massive from the ground up. Today, we're locking in on implementing cryptographic hashes. We're going to build a SHA-256 hashing function in Rust. And honestly, we're treating this as the strict structural blueprint for literally everything that follows. Okay, let's dive into our engineering site plan. We'll be looking at 1. The blueprint foundation. 2. Rules of canonical serialization. 3. Building the hash function. 4. Testing your cryptographic machinery. 5. Essential quality assurance. And finally, 6. Ready for Merkle-trees. Let's get to it. Part 1. The blueprint foundation. Securing the blockchain structure. Remember our previous lesson on project overview and security goals? We're picking right up from there. So, you might be wondering, why do we even need a custom hash function? Why not just throw our data at whatever default hasher is lying around in the standard library? Well, it's a great question. We need deterministic leaf outputs. Without a single, precise, well-documented function, our digital signatures are going to try to bind to ambiguous, messy data. And if that happens, the whole system literally falls apart like a house of cards. We need precision. Which brings us to part 2, rules of canonical serialization, speaking the exact same language. Before we can securely hash anything, our data has got to be perfectly organized. So what is canonical serialization? It's the process of deterministically encoding structured values into an exact, uniform sequence of bytes before hashing. Look, here's the thing about computers. They're aggressively literal. They have absolutely zero common sense. To us humans, a capital A apple and lowercase a apple are the exact same fruit, right? But to a computer, a single unexpected uppercase letter, or even a stray space, completely ruins the whole hash. The byte sequence must be identical, every single time. No exceptions. And this brilliantly illustrates the point. Check out the difference here. On the left, we have the input alpha. On the right, we have alpha followed by a hidden null character. To the naked eye in a sloppy debug log, they look exactly the same. But that invisible trailing character completely scrambles the resulting SHA-256 digest. This is exactly why canonical serialization isn't just some nice-to-have feature. It's our absolute prerequisite before we generate even a single hash. Identical logical values must produce identical bytes. Part 3. Building the hash function. Assembling the component. Time to get our hands dirty. We're moving from the drafting table to the assembly line. Here's how we build it in Rust. Step 1, add the SHA-2 and hex dependencies to your cargo.toml file. Step 2, create your source file hashing.rs and write out the hash_leaf function. Step 3, set up your explicit test vectors in a testing file. And step 4, execute cargo test. It's a clean, really systematic build. Oh, and by the way, if you ever feel kind of rusty on these Rust module setups, definitely check out the other Forge College courses to dive deeper. Now, let's look at the design rules for our hash_leaf function. It has to consume canonical byte slices only. Keep the function pure, meaning absolutely no global state. It should return a 32-byte SHA-256 digest in raw bytes, and it's also super helpful to return human-readable hex strings for debugging. And lastly, never, ever use randomness. So the crucial point here is that this function must be pure and free of side effects. No outside variables can influence it. Zero global state means perfectly predictable outputs every single time. Part 4. Testing your cryptographic machinery. The unbending rulers. You know, in cryptography, we don't just write code, cross our fingers, and hope it works. Nope, we use test factors. Think of them as the standard weights and measures for our newly built machine. Now, what's really interesting about this is how these explicit vectors act as the undeniable source of truth. Look at the inputs: an empty string, a single character A, and the string ABC. We know exactly what the SHA-256 hex output should be for these precise inputs. If your function outputs anything, and I literally mean even one single character different from this table, either your hashing routine or your input bytes are incorrect. Period. End of story. Next up is the determinism check. If you call hash_leaf multiple times with the exact same byte sequence, it must return identical hex and raw outputs every single time. If this check fails, you've probably got a non-canonical serialization issue on your hands. Or even worse, an accidental mutable buffer, meaning your data is quietly changing shapes in the background and just ruining your blueprint. Watch out for that. Part 5, Essential Quality Assurance, Stress Testing. Okay, Even the best engineers run spot checks to catch trivial collisions and gross implementation errors. If a test fails, don't panic. Just run through this debugging checklist. First, print your raw bytes in hex before hashing so you can see exactly what's going in. Confirm your length prefix strings and fixed ordering. Check your endianness, whether your computer reads bytes as little endian or big endian, because mixing those up will completely scramble your digest. Remove any stray white space or new lines hitching a ride, and use explicit byte literals. This is basic, common sense QA, but I promise you it'll save your keyboard from being thrown out the window. I really want to emphasize this quote. Test vectors are not optional documentation, they are the contract. Actually, scratch that. They are the absolute law. Future implementations, external modules, cross-language ports, they are all going to rely entirely on this contract to verify compatibility. You've got to treat your tests as a first-class part of your project's API. Part 6. Ready for Merkle-trees? The next build. Let's move ahead and see how this builds into our next step. This is where we put this giant puzzle piece exactly where it belongs. This single stable hashing module we just built, it is the absolute bedrock required before we can begin building and verifying Merkle trees in our very next lesson. That Merkle implementation will call your hash_leaf function for leaf construction, and it's going to rely heavily on the canonical serialization contract you just locked down today. Now, if you're feeling adventurous, here is a stretch goal for you. Try porting your canonical test vectors and your hash leaf contract to another language, like Python or JavaScript. Why bother? Because successful parity across different languages proves without a shadow of a doubt that your hashing contract is truly canonical and environment independent. It's a really cool exercise. So, what does this all mean? I'll leave you with this provocative thought. If your serialization logic or your hash function changes tomorrow, what happens to every existing Merkle root and inclusion proof you've already built? Spoiler alert, they all become instantly invalid. The whole system breaks. That's exactly why we spent this time building a rock-solid, completely deterministic foundation today. Thank you so much for joining me for this Forge College Explainer. Keep experimenting, keep testing your code, and be sure to visit forge.college to continue your Web3 learning journey. Catch you in the next build.